I miss the lighting.
Speech chair.
Oh. Hey, Pavel.
Proposal says, but play a bit more if it causes problems. But I think we can go ahead and get started and more folks can join us. But it is my pleasure to welcome Daniel Apai, who's a professor of astronomy and planetary science with a joint appointment at the Steward Observatory in the Lunar and Planetary Laboratory at the University of Arizona. And we were just talking about it since 2022. Dr. Apai has also been serving as the interim associate dean for research of the College of Science there. And you received your PhD in astrophysics from the Heidelberg University, and your research interests are in exoplanets and astrobiology. So I'll turn it over to you, Daniel. Thanks for coming and talking with us today.
Thank you, Joe, and thank you all for joining. And it seems like I was here a few months ago, but it was actually 1.5 years ago. It's time to come back. And then last time I talked about a different project. This time I wanted to introduce our Bioverse framework to you, I think, and I hope that this will be of interest to many of you, especially because this is very much basically a framework developed to bridge fundamental research modeling hypotheses about habitable planets and then mission design, and hopefully it will be of use. So this is coming from a larger collaboration. We have now about 5 papers out, another 5 papers in preparation. So there's a number of people who have participated in different projects. I listed most of them down there, and I will point out some of the lead authors in the papers as I move forward. So the title is Bioverse, which is the name of our framework, and then I changed a bit of title, but it is the same topic: mapping exoplanet science questions for the next 3 decades. So which sounds like, I think, very ambitious. I will show you why I think this is actually possible to a significant extent and why that is useful to do. So before jumping into Bioverse, I wanted to set the stage, and then just some of you may be aware of our Alien Earth projects, others may not. So I thought it may be useful just to introduce this to you too. Alien Earth, and this is a project I will particularly emphasize our strategic work to support exoplanet missions. Over now, it is a decade. We turned 10 recently. So Alien Earth is the indirect continuation of Earth and other solar systems. Both of these are large NASA ICAR grants. Each of them were $6 million grants. EOS ran between 2014 to 2020, 2021 with an AUKUS extension, and then we were able to win again an award and continue, fortunately, with the Alien Earth, which is now about halfway. So these are exciting. We are among the large teams within the new, I guess less new anymore, ICAR program that is supporting NASA astrobiology. This has also been supplanted. Of course, when you have such a big grant, it provides the stability and provides a backbone for the community. So we were able to leverage this with other grants too. The key question that we are exploring is which nearby planetary systems are likely to harbor habitable planets and life, which is, I think it's an easy to understand question, but a difficult one to answer. You really need to basically fall in a whole variety of disciplinary knowledge and methodology to approach this question, which has been really interesting and fun. If I were to give away our formula for what I think made our proposal successful, was integrating not only cutting-edge research, plant formation, theory, observations, but also experiments on cosmochemistry, return samples with exoplanet discovery and demographics and characterization, together with scientific hypotheses and then also exoplanet mission simulators. So from the beginning on, we framed this project as a way to channel, if you like, from data to information to knowledge, all the way to shaping science cases for missions and producing tools and then guidance that is hopefully of use. So Alien Earth, this was just from our proposal. I will not go through all the detailed structures, but I want to point out that we have 4 modules. We have 12 projects organized in 14 4 modules. The first one explores the conditions and timeline for planet formation, and this combines observational studies with cosmochemical analytical studies, and theory. And then what we learned from that helps us to advance protoplanetary disk models that then provides basically initial and boundary conditions for our understanding of how the plant formation pathways impact plant composition that emerges through that formation process. So if you turn the knobs in the plant formation process, how will that impact the plant composition? And then what we learn from that goes into model 3, where we are looking at the habitability and threats to habitability in nearby planetary systems. That includes both searches of planetary systems, understanding dynamical stability, orbital evolution, and then also possible formation pathways. And then ultimately, all of these basically channels into our module 4, which is where we take the knowledge from the previous modules and then combine it with new studies to try to inform exoplanet missions. These include studying also contamination of stellar transmission spectra, refining the occurrence rates of planets, including Earth-sized planets in the habitable zone, and then also including understanding biosignature patterns in populations of evolving worlds, and then providing a probabilistic assessment of habitability and biosignatures. Very importantly, all of this is done, and we continue to do it in the framework of Nexus, the NASA Nexus for Exoplanet System Science. And I will just highlight that this has been a really exciting project. We published now over 210 refereed papers, over 7,000 citations. We don't label all our papers as alien Earth, but you would recognize many of these. Some of our papers have reached hundreds of citations by now, and I think it's fair to say that they made an impact on the field. We organize various meetings, and we have lots of fun collaborators. This is a really nice community. What I wanted to emphasize more, however, is connection to different missions. So in addition to the fundamental research that we do, discovery, we also create frameworks and knowledge and models that then help inform science cases, experiments on different missions. Today, I will talk about Bioverse, which is in the upper left here. That is a mission and survey science definition framework, and that is already informing many different missions. But let me point out a couple of others very briefly. Genesis database is a library of hundreds, actually now about 1,000 simulated planetary systems, where we trace the entire formation and evolution of the system, all the planets basically building up from planetesimals and planetary embryos, their accretion history, volatile content, migration interactions, and running these simulations with different knobs turned at different levels, so different parts of the planet formation are important. So that allows us to basically provide both a forward modeling study of what is the impact of different changes in the planet formation pathway on the emerging plant population, but also an opportunity to work backwards. If you have planetary systems that you find with a mission, what are the pathways that are within our formation models that are compatible with those outcomes? So those are important. We developed also a tool called ePods that was with Heinz Smulders, was a postdoc in our group, that allowed, I think what was the first, in some ways, very rigorous comparison of plant occurrence rates with plant formation models. So that has been important. We have developed a quantitative habitability framework. So this is something that I think is also very interesting, but I just didn't want to squeeze it into this talk too. This was a result working with Nexus, NASA Nexus. We had a science working group. It was one of the first science working group within Nexus that was formed about 3.5 years ago. We worked with a large community to try to move habitability, which is obviously important for the habitable Earth observatory and many other missions too, into more quantitative probabilistic framework that can be used across habitats and different metabolisms. So I'm happy to tell more about that too, but it was a bit too much to put into this one. We have also developed and described the transit light source effect and then stellar contamination models. We predicted that there will be a major challenge for James Webb, and unfortunately we were right in that sense, but it also gave us an opportunity to help improve the constraints that James Webb can place through transit spectroscopy on exoplanets, and then led also to the birth of this very exciting mission Pandora that we are excited to work on. And this week is the Pandora Science Team meeting, which brought me here. Dynamite, I will mention also very briefly. So Dynamite was led by Jamie Dietrich, my Ben was a grad student with me, James Dietrich is also a graduate student, was a grad student with me. Dynamite, what we do in Dynamite is that we looked at how can we predict yet undiscovered planets in planetary systems. So in most planetary systems, you would know 1, 2, or maybe 3 planets, but you are missing the majority of the planets. And so we took exoplanet demographics and a couple of orbital dynamical stability and other first principles based analysis, and we were able to predict the sizes, the location, the periods of planets that are yet undiscovered in those systems. Since the initial paper was published, 2/3 of the planets discovered in test multi-planet systems where we predicted them to be with the right masses. So we think that that's quite important for typical systems, also for a direct imaging mission. And then last Ilaria's group has been working on planetary current traits and demographics within alien Earth. So you may in particular know Galen Bergston's lab studies on Earth. So these are a couple of like big picture tools that we have developed, all of which is open source, and we are very happy to collaborate. We want this to be as useful as possible to the community, and especially for those of you involved in mission design. If some of this is seems useful, please let us know. We are happy to have connected. Here I wanted to tell you more about Bioverse, which is probably our largest framework. And this is aimed at science case definition for exoplanets and habitable worlds studies. So it may be a bit obscure. Why would anybody want to do this? So let me show you why I thought this was important. So I have worked about 15 HST cycles ago. I was at the Space Telescope. I was part of the science policy group for Hubble, and it was a very interesting challenge to try to see, what limits Hubble scientific productivity, how we could make that better. After that, I served in the Exopeg EC, where I led a study group, SEC-15, where with about 40 people, we worked for about a year to try to figure out what could be the biggest questions, most exciting questions that a future direct imaging mission could potentially answer. So this didn't include really any mission simulation, but we have the question, what we would like, what are the questions we would like to answer about exoplanets that we are able to image potentially in the future and characterize, what may be answerable, how we could test these, answer these questions. So I think this was useful. This was for a long time ago now, but some of these questions are pretty long-term questions, and I think I'm hoping that this is useful for the community. One of the things that I didn't manage to do in that report was to, which I hope we could do it, but turned out to be a much more complex question, is to figure out what is the sample size that we need to answer these questions. And there is a good reason for that. That's a really tricky question to answer, but that kind of stayed with me, and that indirectly led to the formation of Bioverse. I also worked with the Space Telescope Science Institute. I was a chair of a fast turnaround committee to provide a report on maximizing HST tests and James Webb synergy, which was interesting because it got me thinking about multi-mission synergies, how information flows between tasks, the supporting infrastructure, ushering candidates to confirmation, to prioritization, to a strong James Webb proposal. And then for that, we developed a simple model for how information and targets propagate through that pipeline of missions. And then finally, I was on the GMT Science Advisory Committee, where we wrote the GMT Science book. Again, we collected interesting questions that GMT wants to work on, and hopefully the US ERT will too program. But in all of these, I think what I was left with is that we lack a proper framework to really define experiments for exoplanet missions and surveys. And certainly there are some exceptions, but in most cases, people build large instruments, 10, $20, $30 million instruments to work towards answering a question, but we rarely can have the kind of level of experiment definition that you would be basically required to do work to propose for time on HST or James Webb. And so the fact that that doesn't exist, that we don't really know what sample sizes we need for some questions, and we don't know what will come out, it's not an accident. It basically is the result of two things. One is that the exoplanet science is not yet fully defined, so this is an evolving set of questions. Second, oftentimes the missions themselves are not yet defined, so it's hard to answer them. And the third aspect is that it's a significant investment to develop a framework that can help answer this. Let me maybe just sprinkle in one more, what I think interesting perspective here. I think we all may realize or think that we live in the golden age of exoplanet science. So this is a simulation that you probably may have seen similar ones at least for the first half. So this was the initial discoveries were, of course, relatively slow, but then rapidly we entered an exponential growth curve. More and more planets are being found. And so we may think we live in the golden age of exoplanet exploration. But I would say that the golden age is really coming in the next 2 decades. This is actually, these are lower limits for what we expect from first TESS, Gaia, Plato, Roman, and this doesn't even include other missions people are considering to build, and it provides mostly lower limits. These will be mostly exoplanet candidates. So I think on one hand, it's an amazing time that I think with more optimistic numbers, you could argue that we will reach by 2045, 2050, maybe even 500,000 exoplanet candidates. So that's very exciting. I think it's also interesting to consider that the vast majority of these planet candidates we will know almost nothing about, right? They will be one blip, we may not be able to follow them up. They will be statistically very, very useful. So we will learn a lot about planetary system architectures, etc., but usually not too much about the planets themselves or really the processes that act on them. That kind of information will come from very capable follow-up missions or sometimes search and follow-up missions that require the largest apertures. I will point out that our planet search benefits from parallel search. All of these are basically space-based, sometimes smaller telescopes that are extremely powerful in searching because they do that in parallel. But the in-depth characterization of planets is mostly still remains a single stream process. So we have to use large apertures and study planets pretty much one by one. So actually, the rate at which we are getting detailed information, for example, spectroscopy on planets, remains fairly constant over time. It's not expanding as much as we would like, which is kind of a limiting factor. So I think putting these together, we set out to try to solve the problem that the community may not have a consistent framework for assessing diagnostic power of exoplanet missions, and then look at also what is the information content that we get from different exoplanet discoveries. So, and this is what we hope to move beyond is now counting numbers of planets, which is always very, very important as an important first step. But then that doesn't always tell you what are the questions that you can answer. So one way to address that problem is to think about basically the scientific method, formulating hypotheses, deriving predictions, and then testing those predictions. And we actually can reasonably well predict now at least many of the hypotheses that we may be able to formulate or we want to formulate, and whether they may be testable. So the goal here is not to determine which mission or experiment can exactly do what, but to provide kind of the parameter studies that can guide prioritization or the synergistic use of these missions. So we built for this framework Bioverse. We also hope that this helps uniform use of this assessment across different missions and surveys. So what Bioverse does is basically it's a hypothesis testing framework that is very modular and very flexible. It creates, if you like, simulated universes. That's probably exaggerating it a bit. We are looking at basically 130 parsecs around the sun and we know all the stars there. We have characterized them. We can generate around each of those planetary systems that are fully consistent with all the statistical constraints we have from Kepler and exoplanet demographics. We can modify the properties of some of the planets to basically represent an injected hypothesis. This could be, for example, that you change the properties or colors of the planets in the habitable zone to reflect your hypothesis about how the planets there should look like, or super Earths, or close-in or further out planets. And then you take that basically simulated universe and then run it through a simulated survey where we can consider the observing strategy, the prioritization, uncertainties, and we will be left with a set of simulated results. And then on those simulated results, we can do hypothesis testing. For example, if we injected, we assume that every planet in the habitable zone will be purple, then can we actually pull out from the data that they are in fact purple, or can we exclude that hypothesis? So And we can do this in a Monte Carlo fashion, so we can run this hundreds and thousands of times relatively quickly. The original paper was, I should mention, was developed, the original framework was developed by Alex Pixel, who was a graduate student in my group, and then he joined SpaceX, so he's launching many of the Starlink satellites and their darker versions. He has done an amazing job here. We have now two other postdocs, Kevin Hardigree-Ullman and Martin Schlepper in my group, who have taken this up, and then they have been expanding significantly. So what are the key uses? So why would anybody put so much effort into this? So we believe that this is very useful for informing and guiding exoplanet survey and mission science definition and trade studies in a uniform manner, in a transparent, uniform manner. We have already actually found in multiple cases where people have overestimated their capabilities by factors of up to 300. So it can be useful to provide a bit more transparency about assumptions. They can also inform precursor observations and precursor modeling. So we can consider what precursor information, for example, extreme precision radial velocity, what does that information add to your diagnostic power of your mission? What hypothesis can you test with or without that? So, but it can also help, even maybe that's the least obvious, precursor modeling. So there's the old adage, all models are wrong, but some are useful. So what makes a model useful? I would argue that a model is useful if it can inform experiments, you can form hypotheses that then are testable, even if not now, but say within the next 100 years. So we can assess which models are providing basically hypotheses that are testable. And I think some of the models out there obviously are very interesting and they may be instructive, but sometimes the model complexity far exceeds the kind of information we foresee in coming in on exoplanets. And in those cases, those models may just not be constrained much even in the future. And then I think also with the low studies of multi-mission synergy. So I think this is very important for exoplanets where we will not have the capability to have as much information as we would like about planets, but we need to pull together information from multiple sources, multiple domains. And so we can assess the power of that and how to best combine that information. So Bioverse itself is modular, it's open source, and it's continuously evolving. We designed it from the beginning on not to just be, okay, I'm just checking if there's something important in the chat, but I'm not sure I see it. Okay, here, I see a heart, so I think okay. So it's basically, we designed from the beginning on not to just support one assessment, but basically a variety. So we have, this is on the right-hand side, you see a list of modules. We constantly add modules for these and we maintain them. This is available on GitHub. We provided a pretty good documentation, I think, Jupyter Notebook examples to help the team start. It was a major investment from our team. So we have 4 faculty, 6 postdocs, 2 grad students, and we hired also a computer science student who helps to clean up the code and make sure that it is better than what we put together. And so that was a good decision. We have now 5 papers published. The last one is on archive, it's under review, 5 in progress, 1 was submitted, another one. So we expect about 10 papers by the end of 2024 and continue this. So I wanted to just not go too much into details, but give you a couple of examples for the kind of science questions we can assess the testability of, to give you an idea of the scope, and then show you a little bit the future and the timeline for this. So one of the first questions we looked at is whether Earth-sized planets in the habitable zone, are they more likely to have water vapor? Is this a simple hypothesis that we could test? And so this was back in 2020, 2021. It of course feeds into this idea, is there really a habitable zone? We all assume and maybe hope that there is one, but can we actually experimentally test it? And there were other mechanisms or experiments proposed to test it. We looked at here in particular, if we had a habitable zone EXO candidates, and they would have an enhanced likelihood of having water vapor in the atmosphere, would it be testable? So I would say that some of these, maybe I should mention that some of these hypotheses we had there, they are not intended to be super comprehensive. Simply, we are matching the models to the kind of data that we foresee will be available, and it turns out that it's difficult to test very highly complex hypotheses. But we looked at what are the most interesting questions that we could likely test. So in this case, we evaluated the testability of a hypothesis where we basically increase the occurrence of water vapor in the atmospheres of habitable zone exo-Earth. And then we looked at two notional design. This was still LUVO-RA, and then we have another mission concept that we consider, the distributed array, that is basically light buckets in the sky that would allow you to collect much more light. And so this is a typical output from Bioverse on the left-hand side. We use these little, let's see if I can, we use these little logos to help the reader distinguish. So this is a direct imaging mission where you separate the star from the planet. This would be a transit mission. The question here is there a habitable zone? And then we have looked at, I will probably not go through all the details here, but we can vary the fraction of exo-Earth candidates with water vapor in their atmosphere. We can also vary the fraction of non-habitable planets that have water vapor in the atmosphere. And then the green shading here, the color bar, shows the statistical power and what fraction of the simulated survey we can actually test the habitable zone through this water vapor presence. And so you can see, for example, I mean, not surprisingly, the higher the probability that your exo-Earth candidates have water vapor, the more likely it is that you can sample it, you can test that hypothesis. This on the right-hand side looks at what is the exo-Earth yield that you need to carry out such tests, and so that can inform sample size definitions. On the right-hand side, the same is basically for a notional transmission spectroscopy survey, and mission settings parameters change. So this is more of a demonstration of what could be possible and a guidance for if you wanted to do this, what sort of mission requirements you would have rather than addressing a specific mission. Next question we asked, is Earth's atmospheric evolution typical? And I think so. The trigger here, right, is that when we look for oxygen as one of the possible biosignatures, one that is relatively detectable and that, of course, provides a good reference. Earth provides a good reference for. The general thought is that at least in some fraction of the planet, this would come as a result of oxygenic photosynthesis. And if you study Earth-like planets in the habitable zone and you look for oxygen, it does make sense to test the most basic hypothesis, is that Earth-like planets, at least a fraction of Earth-like planets that start similarly to Earth, will evolve the same way as Earth will. So we may find that that's not actually the case, or and that's very important information, or we may be able to verify this hypothesis.
Sorry,
So-
Daniel,
Mhm.
when you say only Earth twins, you mean modern Earth twins?
So, okay, where is...
The red curve?
Yeah, so basically, no. So this would be basically what it shows here is the change of the oxygen content as a function of time. And so we evaluated different hypotheses. In one case, yes, there's the only Earth twins, where we said that we also look for false positives, but we basically have planets that evolve exactly like Earth. So that was one version of the hypothesis. We also looked at other versions of the hypothesis where we said that there's a probability that an oxidation event occurs, but they will not be exactly like Earth. It could appear a bit earlier or it could appear a bit later. So we also looked for, we often look for different versions of the hypothesis and see what flavor of the hypothesis would require what assessment. And so generally, this actually builds on an earlier paper with that I wrote with Alex, where we predicted that there would be an age oxygen correlation. Older planets that are Earth-like would be more likely to have oxygen than younger planets, which is fairly similar if you assume that the oxygen really comes from oxygen photosynthesis, which is an evolutionary complex process, and then we need to change the redox state of the planet. So this is just a hypothesis we put forward in the previous paper. And then here we looked at, what would it take to actually constrain that? And then as a function of false positives, you may have oxygen false positives, or a function of sample size, or a function of oxygenation timescale, how does the testability change? So you could imagine that in the case of Earth, right, it took about 2.3 billion years for that to happen. Maybe in some planets it could happen earlier, or maybe in some planets it could happen quite a bit later. So that would impact the fraction of planets that could be in that state. So we looked at that, and then this was the early paper 2020. This was really pre-Bioverse, but it was basically a simpler approach, looking at just the kind of sample sizes that you would need to assess to be able to test these hypotheses. And again, here we worried on the x-axis the fraction of Exo candidates with life. And we assume that if there is life, then eventually it will lead to this oxygenic transition. So that's basically our definition of life here in this paper. And then all those with no life basically will not have that oxygen transition. Also, we allowed for false positives. And then this explores the sample size. In the gray region, it is possible to test the hypothesis. Here, it is not that possible to test the hypothesis. I would say that the precise numbers don't matter that much here. I think unless you have a specific mission you want to compare this to. What I think the big message is that this is the kind of hypothesis I would want to test, and it could be testable if we have the ability to select the sample as well as controlling for the age.
Multiple doses. Multiple doses.
Yeah. That's right, yes. And then you can, basically look at different complexity of the hypothesis. What we also found is that if you have an ability, which is not always the case, but if you have an ability to prioritize targets, in this case, age is an important indicator. So mixing in younger planets, younger systems can help to improve the diagnostic power for basically anything that has to do with the evolution of the planets. And then, that's also kind of obvious in retrospect. If you find many 100-million-year-old planets that are oxygen rich, then maybe oxygen is not produced by oxygen photosynthesis, but by a simpler abiotic process.
At what point is life rare enough that you really can't test it? You seem to have failed to start.
That's right. So basically in this, what's the figure? So here, basically, if you approach to zero here, then as you approach zero, you will basically need an infinite sample size.
So if there's something where there's no emission, even if you have no
Yes.
noise, that you start to really not be able to test things.
That's right, yes. I mean, if life is basically very rare, then yes, then you cannot basically, test hypotheses related to the evolution of life. So you are right. So that's, I think, even in those, so it is useful, I think, to be able to say what is the range within which these hypotheses become testable with the given approach. So we also ran the same with Bioverse, both for transit and direct imaging. With Bioverse, we can do much more detailed simulations and much more detailed assessment than the previous paper, which one was basically just looking at simple statistical considerations. Okay, the next question is, what can we learn from O2 surveys with the ELTs? So the ELTs will also be able to searching for O2 in planets. And we have not found really a proper assessment of what they can really do. We have found a couple of really compelling papers. There's a list of them here that proposed using transmission spectroscopy. In particular, most of these papers, except the Curry et al., which is broader, but most of the other papers focused on the idea that if you can tell apart whether oxygen absorption emerges from the Earth's atmosphere or from an exo-Earth atmosphere, if you consider the radial velocity difference between them. So the oxygen lines that emerge from an exoplanet could be shifted in wavelengths or in frequency space out of the terrestrial oxygen line forest if the velocity difference is the right one. So this was a compelling idea. I think already the early papers by Ignace and then Florian and Mercedes pointed out that it's not easy to do, but it kind of suggested that it's doable. So I have seen a number of groups, proposing that we could look at the origin and evolution of life through this technique, and that the ELTs will be able to look at presumably dozens, maybe hundreds of planets. And I was a bit skeptical about that. I would say that these papers didn't really suggest that, but they were also not comprehensive enough to really show that that would not be the case. So they identified that you need basically to focus on mid-end wars for this to work. But most of these studies really focus on hypothetical planets, assuming that Proxima Centauri is an Earth, and then what could we do there? And of course, Proxima is the closest star, so it's not typical in any sense. And Proxima Centauri B, we don't actually have a mass for it, just a minimal mass, and the expectation is value for the mass is quite a bit higher. So I'm not convinced that that's a good assumption. So we felt it was important because the US ELTs are, and this is an important science case there, right? So what our study did was much more comprehensive. We simulated entire surveys, decades and Eocene and longer operations of the ELTs. We considered actual host stars and point occurrence rates. We calculated and considered the actual systematic and orbital RV variations and values and variations. The previous studies just assumed that there is the right amount of RV difference. We consider target visibility and observability. So one of the big catches is that when people say, this signal is detectable in 20 transits, and each transit is just a couple of hours, it sounds like, that's not too bad. But if you try to do observations from the ground of specific planets when they are transiting, that it can be challenging. So we considered all of that. We then actually simulated, the air mass variations, weather, multiple telescopes. And so to do this, we actually went back and then we recalibrated the Gaia target catalog. So this was useful also for future studies too. So we took, this was a really extensive work by Kevin Harteg-Ullman. We wanted to make sure that the stellar properties we use, they are really state of the art. And so if anybody is interested in that, I can tell you more about it, but I will just move a bit for the sake of time. We also consider the blending of wavelengths, what velocity differences will result in what level of line blending. We consider the celestial positions, RV differences, air mass, and weather. So this is an exciting figure. Let's maybe just focus on the top panel. So that will be probably enough. This shows the GMT. These are all the planets basically that exist. The x-axis shows the temperature. On the left-hand side, there are M dwarfs. And on the right-hand side, there are early M dwarfs of their stars. And then the y-axis shows the average observable transits per year. So in most cases, you just have one or a handful of transits observable. In some cases, you may have up to 8 or 9 transits that are observable. And then we start to consider detectability in the A band or the oxygen infrared bands too. So you could combine these to get higher signal to noise. And then we consider the geometric transit probability, how many of these are transiting. And you see that basically it's from 500 planets that exist in the volume that we probe, we expect about 9 to transit. And so we repeated, this is the GMT, we repeated TMT, ELT, and we consider the case when you would be using everything together. We then also looked at for each of the planets, just generally, how long would it take to build up the signal to noise? So this shows the time required. And so you start to see that these are centuries. Yeah,
But the transit case, the nearest transiting one is TRAPPIST, if I remember correctly, right? And there are no transiting ones that I remember of. So the number of transits obviously makes sense, increase, even for Proxima it's not transiting. Probably.
Yeah, so TRAPPIST you could probably not do well with this method because it's basically sensitive also to the spectral, the host star. We did actually add a section on TRAPPIST on that, right? But yeah,
We are running out of transiting.
there are not enough transitive candidates close enough. That's really there. And I think that's oftentimes kind of when people guesstimate, that's what they are missing, basically this distribution of planets in space. They assume that the planets are closer, they go with Proxima Centauri somehow being the representative, and that unfortunately, what happens here is
2 weeks ago.
You're saying every M-star doesn't have a transiting planet?
And so it's, and you know, it gets bad, right? Because if you can observe, you know, you only collect here light during the transit, it's a few hours. And if you have one transit that you can observe in a year, and you
It's
know,
cloudy.
yes, and it's cloudy. And then if your source is not proximal, but it's not 1.3 parsecs, but say, you know, 4 parsecs away, then you need to integrate 16 times longer, but that doesn't mean, you know, so I think you follow that. So these are basically the survey durations and the number of planets. We simulated hundreds of surveys, so there's a scatter. Sometimes you can get very, very lucky, but this is the typical outcome. So for basically none of the ELTs in the transit for oxygen, that methane may be a bit easier, but not all the instruments are capable of doing that. So, but it kind of shows, I think there was a big discrepancy between, you know, what was maybe the perception of some groups and what, you know, what the reality. And I would say that this is still fairly optimistic. There are still 3-4 other effects that we didn't consider and that we basically made best case assumptions. So we did not consider changes in the Earth's atmosphere. All of this relies on basically the ability for over decades accumulating signal to reach a 3 or 5 sigma detection, assuming that you are not really adding systematic noise. And so, okay, so I think I don't explore this further. I think you go. So this is kind of, I think, something that others could have done, but nobody did it, and the result is not what others would have expected. And I think it's useful in terms of our strategy. Then, yeah, and I would say also that it's not only, the outcome here is not only that oxygen is not good in transiting planets, it is also that we have a machinery. We can repeat this for other biosignature gases. So that if people have other ideas, we did it for higher resolution, we are looking at different wavelengths, we can repeat it because the machinery is.
How about interferometry, we might be able to get some of the basics.
Yeah, so we have done a bit of exploration of interferometry for life.
Like VLT gravity or stuff like that, it might be.
We haven't done that, so if, but that's interesting. Maybe we can talk about that. Well, we did direct imaging. So this is a paper that's coming up today on Archive. Also, Kevin Hartley-Gilman led this. So this is basically doing high contrast combination with high dispersion spectroscopy, direct imaging. Direct imaging's advantage is that you basically are not, you know, limited to the transit events you can observe later. And so we did basically, again, we built on a previous study, but then added XAO modes. It's pretty tricky. Some of these XAO systems are not fully defined. So we worked with the PCS team, the PI there, Markus Kasper on the European side, and then from the GMT side, Sebastian Haffer. So the good news here is that the sample size is somewhat larger. You can see again that the ELT will benefit from a larger aperture. The GMT will be able to reach a smaller set of planets. These planets will overlap. So fortunately, the GMT has a first generation extreme AO system. So there is a first mover advantage, and GMT should be relatively quickly be able to clean up the closest planets. But yeah, once the ELT is online, the second generation instrument suite includes PCS, and that will, you know, clean up pretty much the southern hemisphere for this. So this is basically we can change different size ranges for what we consider. This is a large enough sample that you can start asking questions like increase the current rate of O2 in habitable zone exo candidates. It starts to become, in optimistic cases, testable. We can also, in the paper, there's also a plot where we compared super Earths. Could you check whether or not super Earths would have enhanced oxygen rate? Could you compare oxygen levels between super Earths and habitable zone? And so this starts to be, I think it's exciting. So this is something that could be within reach in about 10 years, depending on the outcome.
Did you say this was on Archive yet, or it's
It's
gonna be on?
today, it's coming out today.
So Kevin gave this talk at AppSciCon, actually in one of the sessions, so, and it was a few weeks, and Miles Curry suggested it was actually a couple of years. So they were talking about this, Miles and Kevin. There are
Yes.
already 6 habitable planets in the nearby and star non-transiting ones. I think this is is promising.
Yes, I would say most of the ones that we know currently are M-SIN-I detections.
Yes.
And so they tend to be lower limits, but yes, I think this, I wasn't quite sure how excited I am about direct imaging. I'm now more excited with it from the ground. Yeah. Now yeah.
Did you, in these analyses, do you factor in the M-SIN-I uncertainty, the probability, like, probability that actually 60 degrees because of those things, not actually Earth's?
So what we do here, we also consider the known radiodiversity detected planets in a separate subsection of the paper. But these figures basically come from planet occurrence rates, so we predict what's out there. And so in that sense, there is no RV information that it is. We consider what is out there and what would be detectable. And there is an overlap with some of the M-SIN-I planets that are in.
Oh, I see.
60.
13.
Most probable information, a random distribution of information.
I thought it was
60 from baseline.
Yeah.
60 from baseline.
Oh, I saw analysis that it was, because it's not random, because you're more likely to detect something at lower information.
With RV, that's true.
Anyway.
But these are planets produced by a population.
Yeah, that's right.
Oh, okay.
Well, we also addressed, we also went through all the known RV planets separately, but it's basically a similar plot. So it's a similar. Okay, just for the sake of time, let me just go 5 times as far. So we also asked this question: are there discontinuities in the inner edge of the habitable zone? So I think this is interesting. There have been models by Caroline Dorn and Tim Lichtenberg, and there are other groups, other models too, but that predict that at the inner edge of the habitable zone, right, you may have a very sharp insolation threshold. And if you exceed that insolation threshold, of course, you may have a runaway greenhouse effect. These particular models looked at basically if this happens and you increase your surface temperature to a high enough temperature, you would have a molten surface, and that would couple your volatiles in the atmosphere to the interior of the planet. And this is a complex model, but they made a prediction. The prediction would be that there would be a significant increase in the transit radius in planets that are in that state. So we have the question, could this be detectable?
How long does this phase, do they say this phase lasts?
So it's a good question. So in some cases, it could last long. In some cases, last less. It will depend on what is the composition of the planet, how much water you have there. But they have, and how close you are to the star. So I think that the magma ocean for TRAPPIST-1s, those were modeled for hundreds of millions of years in some models. And, I'm not, I think this is a good model, and I'm asking a question, is it a testable model? But, yeah. Okay, so I will make this short. So basically, Martin Schlecker led this study. We looked at if you have a transiting planet mission that measures transit radii. Tim Lichtenberg is on the paper. We simplified the model to have a more clear, that we don't have to run the whole complex model. And what we found is that, in fact, this is, if the effect is as large as they predict, this could be leading to habitable zone planet radius discontinuity that could be testable, potentially with Plato, depending on, in large part, Plato's efficiency of follow-up and verification of candidates. So the ground-based setting. We are working on integrating biology into Bioverse. Everything I showed you before was abiotic processes. We have been working with a group of ecologists who have developed and published 3 papers in Nature Communication on planetary scale metabolic models that describe, in particular, methanogens, their impact on the climate, and so that includes a planetary interior model, an atmosphere model, a climate model, a photochemistry model, and a metabolism model. So these are complex models, but they make interesting predictions. We have been, this is the work of Anthony Affolter, who defended his PhD about a year ago in Nice. So in his PhD dissertation buried are 3 papers that we are helping him to publish. And so those are pretty interesting. We put this in the context of something like the habitable world observatory type. What could it do? Could it test? It turns out, for example, the mode of plate tectonics is maybe something that could be testable. And then we are looking at probing metabolic transitions, a bit like I mentioned, the oxygen transition, but there are also basically other metabolic transitions from methanogenesis, for example. So we are working, I'm in part here to work with Noah and Chris on better connecting, building on our new array modules, but then really integrating, connecting to the extent where Chris has been doing over the past 10 years on assessing the yield and performance of space-based high contrast imaging, and so that we can explore what are the kind of questions that, you know, depending on different architecture choices and strategy, could be a direct imaging mission could be answering. So part of this is interpreting reflected light signals, and Noah is doing an excellent work in leading this. So I will wrap up this a bit over time. I wanted to show you kind of the timeline. We have, I think what is interesting is that the next 2 decades in exoplanets is kind of being defined now, because we have a couple of really big projects coming online, ambitious projects, where we can now influence, all of us, the strategy, the choices, the follow-up, and then the models, the precursor information that goes in. So we hope that we will be able to help some of these. And I think you can argue about the years. Forgive me.
Hold it used to be watch dated a little bit.
Yeah, I shifted kind of everything a bit to the right sometimes. They also have like a gradient, so it doesn't have a defined.
You could add tests too. It's supposed to last like 30 years.
Yes. Okay.
I'm only partly kidding.
That's,
That's food for thought.
so, yeah. So we have basically, we already see that actually we can start probing the habitable zone inner edge in the next couple of years, which is interesting. I think with the extremely large telescopes, if everything moves forward, we will start to be able to image some of the closest systems and small set, but maybe if oxygen is common, then we can start testing hypotheses, or we can prove that it's not. And then, of course, the most exciting here will be, you know, HW, because for all the capabilities, that's where you can really start to ask much more complex and more interesting questions. So I will just mention that we built many modules, but now most of all of these different teams, we either built modules or they approached us and we are working with them. We are starting now to look into Roman. We have already looked into that, and I think that could be also very interesting. Most of this is statistical evidence, so we are looking into those. And I will just end with saying again, so we have this Alien Earth team, and I think we created many tools and frameworks that I hope will be useful for the community. Bioverse is one of them that helps with mission and exoplanet survey simulation. I think it fills an important gap between science cases and mission requirements. I can show that it's modular. I will just end with that. I think, you know, considering the information content that's coming from the different surveys, I actually think that it is possible now to think about what will be at least some of the big questions that we can statistically address in the next 3 decades. And we can make choices based on those predictions that can help us maximize the likelihood that we can answer those. So let me stop there, and thank you for your attention.
All right. Awesome work as always, Daniel. There's a couple of questions online I want to get to, and then we don't have too much time, but if there's any in the room or online, feel free to raise your hand. But Daniel Angerhausen asked, how do you quantify the uncertainty of the individual simulated observations for the bimodal questions like no water or water? And how do you include those individual uncertainties when you're computing the uncertainty of your hypothesis?
Yeah, so that's a very good question. So generally, Bioverse is a large Monte Carlo framework, so we have pretty significant flexibility in prescribing either priors to our information or dealing with uncertain outcomes. In one of the projects I showed you actually, I think in 2 projects, we have said that if for, you know, just to simplify things, if you reach a certain signal to noise in a continuum, then you are able to determine whether or not it has, you know, Earth-like, for example, oxygen or water abundance. So sometimes we can just say that the experiment or the measurement results in a clear answer, and then we can propagate that forward. In most cases, we can assign an uncertainty. So if we, for example, want to measure an abundance, we can simulate those. We have collected two different atmospheric simulators and then also signal to noise calculator. So we can provide an uncertainty on measured values too. So depending on what is the question, what is the maturity level of the concept that you are dealing with, there are different choices that are the optimal.
Great. I'll take one more from online and then we'll go to the room next. How do you, Vlad Ayarpetian is asking, how do you define Earth's twin in those earlier?
Okay, yeah. So usually, in most cases, we don't work with Earth twins. There was a very early paper, which was really just a letter in which we proposed the age-oxygen correlation. So the point of that was really the age-oxygen correlation we proposed. It was not aimed at a really detailed simulation of outcomes. In that early paper, we defined Earth twin as an exact copy of Earth that is evolving exactly the same way. So the great oxidation event occurs at the same time as for Earth. And that's generally, we don't, general models are more broader than that. That was one particular case where that was defined.
Thanks.
Can I just ask? Hello, Daniel. Yeah. So my question is about are all Earth twins with the certain level of oxygenation around a G, K, and M dwarfs are equal? So that's because it depends on the star. So how would you define the Earth twin in relation to a host planet or a host star?
Yeah, so basically in that model, right, we had considered different layers of complexity in the hypothesis. The simplest one is that every planet is an Earth twin. That's where we started. It was just a null hypothesis. Those were actually, and then we allowed for increasing complexity. We allowed basically for, planets not having at all oxygen transition. We allowed for them probability to change the oxygenation lifetimes, oxygenation timescale. So actually our model is pretty broad. It's just our very first simplest model is where we said oxygen twin or Earth twin, and it makes sense to start from there. But you can basically within our model runs, you will find guidance on what would happen if it happens much earlier or much later.
All right, let me grab one last quick question from the room. Is there anyone in the room who has a question for Daniel?
Have lots, but.
Not quick ones. All right. Well, if not, we're at our hour. So I think Daniel's here, has some meetings already, I think, booked up for this afternoon. But if you want to chat with him, maybe grab lunch today. But let's thank Daniel again for the great talk. Thank you. And thank you everyone online for joining. And Daniel, there's a couple more questions in chat. So I don't know if you want to just take a look at those and maybe get back to people at some point.
Yeah.
All right.
Perfect. Thank you.
Yeah, of course. I'm gonna end the meeting though. Thanks everyone for coming out.
Perfect.
We can take some notes.
Yeah.
Thanks for the talk, Dan.